Yeah, so it will be kind of improvised since we chose the subject yesterday evening just before midnight. So don't expect slides, don't expect things like that, but I have ideas and stories, so it should be long enough. Cut me if I'm too long, okay? We will talk about thermodynamics of software with an interrogation mark, because I'm not quite sure we're there yet, but I will speak about all the problems that still need to be solved in this space. The first thing is that I'm really happy to be here just after Mel Conway, because all this thinking has been triggered by first being in contact with his ideas. And the starting point was in 2013 at Build Stuff, in the cab to go to the venue. I was sharing the ride with Peter Hinchens, late Peter Hinchens, and I was just explaining to him that, yeah, I try to adapt the way I'm working with my software developers so that the things go smoothly and things like that. And he told me, yeah, you know, the Conway's law. And I was like, yeah, Conway's law, I'd already heard about it. And I knew the joke. Do you know the joke? Yeah. This is the joke. This joke. I really like it, okay? I won't interpret it. It's just here, okay? But it's so true. So that was the joke I knew, and I say, yeah, so what? And at that point, he just gave me an hint. He told me, yeah, you know, people think you have to suffer Conway's law. Because here, when you see that, you can, in most part, expect the result to be quite bad. But he told me, yes, the thing is that you can actually take the form of the system you would like to end up with, and then change your organization so that your system will shape this way. Use the Conway's law proactively, okay? So the law, the initial formulation of the law is something like systems tend to shape like the communication structures of the organization that produce them. It's not exactly that, but I should not be too far. But the other way around, create your communication structure, and you will end up probably with a system that will go with that. That sounded like a sound advice, and I started to try it, and actually you can see quite fast the result. But then I was starting to think, yeah, it works, but why? What's the underlying principle? We can see that, yeah, there is some meaning in that, but I needed an underlying principle, and I started to think about the fact that we were actually always trying to solve the same problem. But the Conway's law is a specific twist in this problem. The thing is that you have a system, and it will tend to probably degrade over time because chaos, because entropy, okay? But there are some people working on it that will give shape to it. So you have these forces that act on your system. And the thing is that usually the forces acting on the system are a bit weak. For instance, you have your users, they want a new feature, and it should produce a force on your system. But this force is a bit like trying to pull something. Can you do that for me? And it's not direct force on the software because the user wants it, but they don't do it. The developers are the ones that are working on the system, so they are the ones that do it. And in doing this, when the system is a mess, they lose a lot of energy trying to modify the system in the way they want. This is what you can call friction. Okay? And friction is about losing useful energy as heat. And so the developers feel the pain of trying to move the system in a direction with high friction. So what they do is that they put other forces to try to reduce this friction as a feedback force. This is a force feedback, okay? Other part of the external interaction of the system, like user wanting some change, are not feedback force. They are things like trying to pull or something, but they don't act on it, and it's very indirect, and so there will be other problems. So I started to think about all this question of software as being that thing that we try to shape with friction. And 2 years ago, or last year, I don't remember, at Handcraft in Paris, I met, at that time, Carlo Pescio. And Carlo Pescio is talking about something very interesting. He's trying to build a physics of software. What is the physics of software? When we think about software and about time, we see the runtime. Runtime is you have written a program, you run it, time is passing through your system, okay? And there is a lot of interesting things happening here, but still there is a full part of this problem that seems very, very, very static. This is that you have one version of your program. What I want to look is about the motion, not of the runtime, but of the software itself. What Carlo Pescio called not the runtime space, but the artifact space, the one that contains the source code. But more than the source code, actually, source code is just an encoding of the knowledge of the people that work on this system, okay? And today, your software is in one position with one shape, and in the future, it will be somewhere else with a different shape, okay? And it will not act just like is it in this shape, and it will be there. You will have to move it from here to there, and to that, you will have to act some forces on it to push it in the good direction, okay? But there are a lot of things that appear when you start to see your software evolving in time as a physical object, is that you can start to make interesting analogies. For instance, what happens if you start to push your software in a direction, like we don't go fast enough in that direction, and then it starts to move, and then, whoa, it's just going very fast in that direction, but you want to stop there. At some point, you will have to restrain it from moving too fast because of inertia. So it seems to indicate that maybe there is a notion of mass, okay? We were talking about friction. Friction, you have your development team who wants to go in one direction, but moving in one direction is easy, and in another direction, it's hard. So you can see that you have several axes, several dimensions of move, okay? For instance, your software is easy to extend in one direction, but it's hard in another. That's a problem. Your software is easy to operate, so you have your operation teams that are always on it, and it's running really smoothly, and you can do whatever you want. But you can have a problem, for instance, that it's difficult to evolve when the customers want some changes. Different axes, okay? And the question is then that your goal is to try to minimize the friction on all the axes where you will need to change. building software and evolving it becomes just trying to optimize your this function so that you know, if you know where you want to go, you look at the path, you see where the friction will be, and you can compute the path with the lowest friction. Would that be cool? It could give you really good hints. So when you start to unify all this, we can start to go back to what we're usually talking about to see how it fits in this picture. This thing, I call it something like a generalized Conway's law, a bit in the same way that the relativity theory is some kind of small part of a bigger relativity theory, more general. Here, Conway's law is talking about friction in one of the dimensions, which is people working on the software. They are part of the problem, and if your software doesn't share the shape of your development team, bad thing will happen because people have to communicate often because they are working on a very close integration point, but they are in two separate buildings. Can it go fast? Yeah, today we have better tools to work remotely, but still, it will be a bit more complicated. It creates some friction. On the other way, you have two unrelated parts and they are exactly in the same building. You will surely see quite quickly new interaction appearing that will make it harder to move things apart, okay? There is a question of alignment, okay? But let's take another axis, and this one will be the axis of your users. Their users are doing their job, okay? Great. And you create a software system to help them in their job, and for you, their job is what we call usually the problem space, okay? Is anybody familiar with the notion of problem space and solution space? Maybe not, but you will quickly understand. We have a problem space. In this space, you have the domain, people working outside of your system, and the thing is that if this thing was totally static, it would be easy, but this thing is also moving. And you will have to, on your side, to make a model of this moving thing there to make it run and take decisions. Do you expect that if the shape of your software is totally different from the shape of the way your users work, will it be easy to change your system when the problem space, your users' way to work, changes? Oh, the probability is not zero, but I think it's something in the order as trying to take a box of matches, throwing it in the air, and expecting them to fall aligned in the box, okay? It's a probability that's not zero, but actually really close to that. So if your system is not, it doesn't have the shape of the external system that you're trying to work with, a small change in your problem space will always, statically, lead to a bigger change in your solution space, in your software. And here you're losing a lot of energy because users say, yeah, can you change that? It's easy, we do it all the time. And then you say, yeah, but in my system, actually, it's not working like that, so it becomes very complicated. But when the things are complicated on the other side, don't expect them to be easier on your side. So you're always losing more energy than necessary. When your systems are aligned, they have the same shape, they work the same. A change is always proportional to the other one. So you have less loss of energy. And if you have listened carefully, you will just have recognized domain-driven design. Domain-driven design is exactly that. This is a technique, a tactic to address the problem of aligning the shape of your system on the problem of your users. And we have a lot of cool tools in domain-driven design to do that, like bounded context, ubiquitous language, aggregates, all that are smaller parts of this solution. You can see that, for instance, bounded context is about removing the friction by drawing some big sets that go together, so you create more consistency inside the concept, while aggregate is talking about isolation to be consistent in time, and all those principles. But all the way is that if you cross those boundaries, it will be inefficient, and you will have more friction at some point. There are also other axes where things can change. For instance, operation I was talking about. When you have a team that do only operation and people that give them, you have a problem of responsibility. That usually the developers won't do things for operation because they don't feel the pain, so there is no feedback force. And so your system will not be operable. You have to think about things like security, because your system is working with the outside world, and in the outside world, you will have bad actors that will try to break your system. And you will have a problem of scalability. If your system is growing very quickly and you don't shape your system for that, regularly the friction will raise as you go on, because your system is not shaped to grow, okay? And you can see that each of the things we are talking about, where we are talking about architecture, can appear here. It's all the non-functional problems that will actually be new axes that can cause friction in your system. When I say reduce the friction, it's the overall friction, but understand me correctly, I don't say that friction is always bad. For instance, there are directions where you don't want to move, increase the friction in that direction. It can be useful. But overall, you want to reduce friction in the direction you want to move in with and the shape you want to take. And in that process, you will see other forces like tensions on your system, things that try to move it in different direction both ways. You will have things like pressure, where try to compact things. You will have some torsions, and all those things, your system has to be fit for all those problems that can arise. But just seeing it visually really start to help to understand when things go wrong, to spot where the problem comes from, okay? So this idea of energy push into a system to make it move or not lose it as heat is already something that can, I think, help us to understand what we are actually doing. We're not usually writing a single version of a software and then, yeah, it's done. Thank you. Goodbye, I will build another system. It's not the way computing works. We have living systems that will move in time and that we will have to change, and we have to understand that. So physics of software is the idea that we will need to identify those forces, and we start to have the analogies, and it's interesting, but we will need something more, because physics without a measure is the same thing as alchemy compared to chemistry. Okay, so with alchemy, this is by the way one part of the topic Mel Conway was referring before. We want to remove this from the priest and to start to make science. Okay, but until now, I've not read much about this question of the problem space moving and how we can interpret it and measure it. We have a lot of things, a lot of math on runtime, on the algorithm, things like classes of equivalence between problem, all the work by Turing, complexity of algorithm with a big O notation, all that are useful tools that enable us to do math on the algorithm and things like that, but we don't have the tools on the organizational part that is needed for us to run our system further in time. So what do we need? This is kind of call to action. Maybe a start of a research program, okay? Today we have alchemy with some recipes that people keep or sometimes share, give some result, but when it don't, everybody says, yeah, I didn't say it worked all the time, I don't know, okay? This is not the way you do math. In math, you don't say, yeah, when you make an addition between numbers, it usually gives this result, but sometimes, I don't know. Actually, sometimes it fails, but we don't really know when. It's not the way you build science at all, okay? So let's stop the alchemy and let's start to build something bigger. But the problem is that for that, you don't create laws just like that out of nothing. Just think about Newton trying to understand the law of gravity. What did he do? He has been looking for long at things falling. And they had something we don't have. They had geometry, and with geometry they had a measure, okay? And we don't have that in software for now, because we are just starting and it didn't appear. So we even don't have on this point the things that the ancient Greek created, and only centuries after that some people started to do real physics. But in between, something interesting happened, that people started to do some ballistic. And ballistic is almost like alchemy, but to physics. It's that you take, at the beginning, they were just make drawings on drawing points to see the shape, and they started to see that it was something common between that, until the point where someone look at all those shapes and say, yeah, I know, just constant acceleration. So then you can use math, and you have your formula, and it's working. That's great, okay? We don't have that. So we have to start to take measures on the friction on the axis, document them, and talk about them. And then we will try to find the schema. We'll create a naive model, and we will have difference of scale. You know, things like before we had unified measure standard unit, people were like, yes, he is 5 feet tall. Yes, but you have small feet, okay? You cannot work like that at some point. But starting to have at least a notion of distance, even if it's not always the same, you start to get a model of what you want to do, even if it's not really solid, it's better than nothing. Because when you have a bad model, what you can do is trying to improve it with new samples that don't fit in the model and change it to fit those things also. And sometimes primitive naive model is enough for most of the problem, and you can stick with it. For instance, in physics, the Cartesian space of Newton physics is enough for a lot of things. But at some point, we reached the limit, and we had to develop the relativity theory. We had to develop quantum theory when things were really small, but when you're not in this case, it doesn't matter, it works, okay? So there will be some places where we will find counter example to those rules that we start to see, but we start with a model, and then what's cool with a model is that it should be predictive, and it's predictive, you can take action, and then if it fails, you can criticize it and try to find the way it fails each time so that in the end you can refine it with a better understanding of what is happening, and getting to something that works finally all the time. Why do we want things that works all the time? Math is used everywhere because in math you have invariants. And what do invariants give? They give guarantees. And with guarantees, you can have trust. Okay? You can count on things to work the way they do. Can the other people in your company have trust in your ability to change the system the way they want you to do? They need a lot of trust, because today you have small guarantees, okay? So it's just like act of faith. I love you, you have done great things in the past, I trust you, and from here, yeah, maybe you will succeed. I expect that. But can you show me that it will work? No. Yeah. So we have to try to start to build these things. And having this idea of forces and all that, in my opinion, is a way to start to build something solid and consistent in time, and will help us to build better systems, moving in time. That's the end of my talk, but I'm still here to exchange about this idea. This is not a final, definitive talk about the subject, as you've seen. I just want to share this idea. You know why? Because it helps to scale brains. Sharing is the way to scale brains. I have this idea, and my brain is not good enough to find all the answer. I can assure you that. But know that it's also everywhere here in the room. You can start to think about it too, and then we can start to try to challenge all that and find what is stable, and we will get to a result, okay? So thank you for listening to me. I know that here I'm asking more questions than giving answers. So yeah, maybe I could be considered as a cheater, but I think it's important question to be asked. So I want everybody to know about it. Are there questions? Yes. Yeah. On what? Yeah. Yeah, yeah, yeah. Yeah, with Carlo Pesio, we were wondering about trying to find something that we could call a topology of software, where actually things that have the same shape are actually the same. You know, things like equivalence is equal to equality or something like that. You can create classes of problem that after that will be the same, and then when you have different things, you can start to see passes and things like that, and so then you can start to have things that looks like measure and things like that. Difficulty here is that probably this space will not be flat, and where dimension will not be orthogonal. We probably will be more on things that have really strange shape, you know, four-dimensional space. You know, for instance, spaces like Euler space. This is a space described by the relativity with time and space interrelated in a quite strange way at some point. We will have probably things like that. So distances and things like that will be hard to spot. But first, if we can start to make classes of problem, we can start to group things together and say, oh, this whole thing is actually exactly the same thing. But we have a lot of solution and a lot of accidental artifact in our solution, like we are working on different languages, but any of these languages will ultimately be transpilable to Turing machine. So where can we consider that the program are actually the same? Yeah, but the same thing will happen at some point with the structure of your artifact space. I mean, with your IDs encoded as a program. We will be able to say, yeah, it's the same thing. And at that point, we can say that the motion and all those things will be in the same direction. And then the small accidental things that make them different will be part of the friction that can happen, and you will try to find a base language or something to reduce that friction at some point. But yeah, the first problem is topology. But to have a measure, because if you don't have the measure, you cannot go after that. Okay. Time passing, we have measure, so this part is easy, but we don't have a space. Yeah.
Just a moment. We have a microphone. Speak into the black thing. Keep it close to your mouth.
Yeah.
If you speak about ballistics,
Yeah.
I think I don't know the history back there, but ballistic is more like a technician that use the weapon.
Yeah.
So as a simple developer or business manager or whatever, if you take measurement and try to draw the software, the engineer team, and the organization, because it's not only software.
No, it's not only software.
It's a lot of
it's larger than that. It includes people working on it.
If we try to draw it, even if it's not comparable and we don't draw everything in it, but if each team here try to do it and perhaps communicate with someone that will try to find some research, it could perhaps be an help because we can start to have drawing of ballistics.
And actually, usually you don't have to draw any each individual people to understand how it works, because the same way as when you are doing physics, you are not moving atoms everywhere all the time. Sometimes you just say, oh, I have a solid. It has this mass, okay? So in this physics of software, you will also have a difference of scale to understand your problem. So some parts can be at very small scale and you will look at details, but it should also work for bigger scale. And probably it's easier to go from big scale first with large movement, general movement, than to start with each detail and it's trying to understand how it works. Trying to produce, the people didn't start with the atom in physics. They started to think that they see, that they move, and then refining smaller things and things like that, we end up with something that is still very solid when we reach a small scale. So, but the idea of ballistic is that before we had the math for and the physics for the motion of things falling, they already wanted to throw things at other people. So they had to find recipes, okay? So they started to try to understand what was the pattern, so that when I throw the stick, will it reach my foes, okay? So, and at that time, when you throw something, you were in a range that was quite large. And as the measure were repeated, the range and the probability to hit the target became better and better. And at some point, we had the math for that. And once you have the math for it, you can compute anything and know very precisely where you will end. But first, just drawings. It helps to think. Yeah, take the mic.
To find patterns of how to say things are the same or different, then we need to have ways to compare them, as you say.
Yeah.
And so we need to find patterns or classical shapes.
Yeah.
Right. But before you find that, you need to find on the measures on what you will say this is the same or this is not the same, right?
Yeah.
But if you find all those measures, how would you collect enough data to find those patterns then?
The thing is that, the thing is that probably at first we will measure things. You know, the first measurements were probably like, oh, it's hot, it's cold, and it's in between, you know. But it's already better to have understood that there was kind of scale, even if you don't know exactly what it is. You don't know that P multiplied by V, pressure multiplied by volume is equal to, and you know the rest of the formula. But still, you start to understand that there is a scale, and even if you cannot precisely say 100 degrees or 0 degrees, and that there is an absolute minimum on all that, you start to see things take shape. And after that, you can say, oh, when you talk about this hot, this is the same as when I talk about this hot. Okay, let's give a value to this. Okay, and this is bigger than that. Already, even if it's not very good, know that you have a scale and that you can compare things on it. It's really better than nothing. Okay, so let's try. I don't say we will succeed in our lifetime. I don't know, but just let's try to go this path to understand this problem. And probably there are already a lot of parts of the solution everywhere. Just people are maybe not yet thinking to try to put them all together to build something that is more unified.
Okay, so kind of to add to previous questions, when you were saying about Newton finding his laws, he was based on geometry, and I was thinking like, maybe you already have something to be based on, maybe it's just not improved, and it was like there is static analysis tools that can be, if not geometry, that can be at least of our arithmetic. And they just are not perfect, so maybe we should try to improve them.
Exactly. Because often in physics, the static will give information about the dynamics. So let's start from part of what we have. And then you actually dynamic is just the evolution of time in time of static. So it causes a lot of problems, but static analysis can already be something. Yes, good idea. I like it.
Thank you. I want to ask about accidental similarity versus inherent similarity. One of Newton's great insights was to notice that not only do falling balls and planets behave in the same way.
And that was probably not accidental.
Right, they behave in the same way for a very good reason. And then and then it's reasonable to assume that other behaviors will be similar because the behavior is not accidental.
True.
And my question is, while it's true that the metaphor of physics and friction and thermodynamics to software development is an extremely useful metaphor, are there reasons to assume that software behaves like physical systems inherently? And then maybe other behaviors about physical systems, I can say they are true about software systems.
The idea is probably we will not finish with someone that is with an isomorphism between physics and software. That would be really, really accidental, I think. But the idea with physics or software, as it is for now, is that there are some similarities that start to make sense. But there are also a lot of glitches in the model that are not good. But the thing is that at least we are starting to talk about a model. When before we were just looking at things like, I don't understand what's happening. So here, you can at least say, my model is good here and it's not good there. Let's find a better model. So we will have. But on the accidental thing, and one of the hard things that we discovered at the beginning of the 19th centuries is that there are things that exist and that are true, but for no particular reason. This is a Gödel's theorem. They are true, but it's totally accidental. So maybe software development.
is
one of them, but we'll not stop to try to find something. Anyway.
Thank you.
Yeah.
We already have quite a lot of work in type theory and theorems which can be derived from, for instance, the signature of a function by Philip Wedler. Do you think your work on building a physics of software
can
rely on this work done already?
In some parts, yes, probably. Because of what was said about static analysis. When you have a good and sound theories like that, that are stable and that give good guarantees, at least you can start to know something. If you read Carlo Specio's articles, you will find that there is a lot of things about the statistical analysis and the structure and the way that some structures are easy to change in some direction and other in other direction and things like that. And so this is this interaction with the type theory. But the implementation is not the only problem we have to address. So it will, of course, be only one part of the solution. Yes.
Thank you.
Yeah.
Hello. So I think it is interesting to compare the artifact space with physics comparisons.
Yeah.
But did you choose thermodynamics specifically as a discipline of physics? Why thermodynamics more than, say, mechanics? To me, your examples makes me think more about mechanics. Because
excuse me, finish the question.
Friction is a phenomenon of just simple mechanics. So in what you said, I didn't see anything specifically about thermodynamics.
Yeah, so the thing is that this is about, there is something about the chaos that will grow when things go without trying to put order in this, with the notion of entropy. I don't say that this comparison is especially sound, but it was a good title, so I chose it. But no. One of the other thing is that I will start to try to find what is something like an adiabatic transformation in software space or thing like that. You start to try to think of your software as a liquid or a gas or things like that, and you will see some shapes. So yeah, it's very fuzzy for now. It's a call to action. I don't want to do this alone. Okay. I know more. I need more people who know more about thermodynamics to have something like that. Okay. So yes. But there was this idea of yes, chaos, heat, and loss of energy that made me think about more thermodynamics than motion and things like that. Okay.
Okay.
Hi. Yeah. I was just wondering that, well, thinking that in physics, numbers and measurements are usually done in an isolated space, and things don't change. And even if we do project them into the real world, we take deviation into account, and we have these numbers, and measurements will be the same every time, again and again. We have, if they are not the same, we do know that we lost this amount of energy, stuff like that.
Yeah.
And I just think that this is really hard to project into software development, and especially changes in the domain. Yeah. Because in the domain we work with people, and even the changes within the domain are very random.
Yeah.
And very hard to, I mean...
The problem is that we have a logical space, not a physical space. And you know the story. Theory and practice are the same in theory, but in practice.
Yep.
Yeah. So yes, when you will creating the theory won't, in a lot of cases, won't give you the exact result, but it's the same with physics. If you if you don't take into account the resistance of the air, the wind, and all that, you won't end up with the expected result, of course. So. Yeah.
And the corrections are the same over time, because we know that if there's a deviation of 2 degrees with our isolated space and the environment around it, we know how much energy will go to waste. If there's wind added, we can take that into account, and we can measure the wind. And
but I think this is the case because young people are making some physics research for the last 400 years. Okay, and we started computing.
Yeah,
So
it's brand new.
At some point, at the beginning, the models were really, really naive and forgetting a lot of things. Okay, we're not ready at that time to launch a rocket in space at all because too much parameters that we could not take into account because we just didn't have all the small parts of the model needed to be ready to do this. So at the beginning, yes, we won't launch rocket in space stuff. I don't know in space with this model. But if it already gives an idea of directions and things like that, and the force you have to apply to be almost at the target, it's better than having just no idea.
I'm just kind of worried.
In 400 years, we'll look back and say, okay.
My concern is that 400 years ago, the forces of nature and everything was exactly the same. We just didn't have the knowledge.
Yeah. Is it the same with people? Yes and no, probably because we don't have enough time of experience yet, but it also seems that maybe it's very hard to predict at the small scale, but at big scale, some patterns happen all the time. And you can see another similarity with physics here is that in quantum theory, when you start to look at a single atom, you cannot say what's happening. Okay? But globally, it behaves always the same.
The result is the same, yeah. Okay,
so,
thank you.
Two questions. Yeah. And if you have other questions, I'm here for the next 2 days. So.
I think we already have some useful results, which are probably intuitively obvious to most people in this room already. Yeah. We already know that larger systems with a greater mass exhibit more inertia, and they're harder to move in any particular direction.
Yeah, the size of your artifact space is kind of mass.
In the same way as everybody 1,000 years ago knew that apples fell off trees, right?
Yeah.
We know the intuitive result. We haven't quantified it. Yeah. So I'm relatively optimistic that we can make progress.
Yeah. No, there are parts that are moving faster than others, I think, in everybody's head.
Hi. Do you think we will have enough time to move on that field? Maybe before the machine, deep learning stuff will eventually find other ways or other proposals? It's a little bit of sci-fi. But
no, I think it will take time, but we will have to find it, or maybe the machines will find it before us. I don't know. No, I think it will take a lot of time.
Or maybe computer science is a little bit like Quantic. And even the creator of Quantic can't define. He said he can't understand well properly.
Sure. Yeah, we won't probably understand every detail, even in the end.
I'm sorry.
No, it's we have to finish, but we can talk about it after. Sorry. Thank you for your questions. It helps me also to start to be able to give more advice and point of view in the next presentation. So thank you very much.